It's my great pleasure to introduce Professor Marjan Sarjani to all of you. She's visiting here for the day. She is a professor at Mälardalen University in Sweden. And her area of expertise is programming languages and analysis techniques for networked and distributed systems. She has worked for many years on what we would call here domain-specific language. It's called Rebeca, for the kinds of systems that you see here on in the title of a talk. And today she's going to present to us some of her work and hopefully establish connections with all of you guys and for future collaboration.
Yeah, thank you very much. Thank you for having me here. So yeah, I'm going to tell you about what we have been doing, asynchronous reactive models, and the analysis that we have been doing that is actually event-based analysis of networks of actors. So this is my background, you were asking. So now I'm in Sweden. I'm also part-time in Reykjavik. And I had many collaborators all over the world, the Dutch people, and these are the actor community, Caroline Gohl and now Edward Lee, and the model checking community, Christel, Holger, and okay. So what I'm going to say, the message of my talk is our Rebeca, the actor-based language, and how it is providing a usable and also analyzable model for distributed, concurrent, event-based asynchronous systems. So you can call this domain, you can call it a domain-specific, but this is actually a very large domain, so contains many applications. And I will show you, instead of, I'm not going deep into theory that much today, unless you ask me. I'm going to show you mostly the applications that we use the Rebeca, and I show you how and why actors are friendly and how they can be analyzed. So our focus is on modeling of networks. So they are asynchronous and event-based, and we also deal with time and uncertainty. So I don't know how many years, like for 10 years, we just had Rebeca and untimed version of it, something like what you have in P. And we used it in many domains. And then in 2008, we moved towards timed Rebeca, and I will start showing timed Rebeca immediately. Because we noticed that everyone is asking for time properties nowadays, and also performance. And then we added uncertainty and probabilistic models. And recently, we are moving towards adaptive systems. The work we have done with Edward at Berkeley, it's on adaptive systems. When you are dealing with change, something has changed and you want to deal with the change. And again, recently, I'm working on the interface between cyber and physical. I still have to learn a lot in that domain when we want to mix discrete and continuous world. And for analysis, the focus has been on safety and performance. We are now looking into security and privacy, but we haven't done much on that. So actors, probably you know about actors. This is a reference model for concurrent computation. And we have concurrent distributed active objects. They're very much like what you have in P. And it came from Hewitt as an agent-based language in MIT AI lab. And then Golaga introduced it as a concurrent object-based language. And people in SRI and others like Caroline Talcott, they made the formal basis and formal semantics for it. So why I've not been in any of these groups, so I didn't inherit actors as the language that I have to use. We looked into different languages, process algebra, automata, Petri nets, and other kind of modeling languages. I wanted to focus on concurrent distributed systems and also formal verification, bridging between these two, have some kind of robust software in distributed.
Actually, can I ask you a question about this? I find that the research community is split between two kinds of people.
Mm-hmm.
One of them calls it the actor model.
Mm-hmm.
The other one calls it communicating state machines.
Communicating state machines.
And
Okay.
do you have any insight into how this bifurcation happened? They all seem to be roughly the same thing to me.
There's another community which call it concurrent objects.
Concurrent objects.
Objects. That's the Simula lab in Norway.
Okay.
So they are also as old, or maybe even older than Actor,
Okay.
from 1960 something. Yeah, concurrent state machines they have state machines. Actors were functional in the beginning, so they were Hewitt actors. It was a functional language with no state variable. So I made it. My version of Actors, Rebeca, is state-based. I have variables because my target were programmers. I wanted software engineers to work with my language. So.
But even for the functional language, the state is still there. It's just passed into the continuation.
Yes.
It's represented as a variable.
That's true, but it's not. It's not as intuitive as
Definitely.
the programmers. Yeah.
I think another difference is the question of how to create or delete actors, and if this is part of the model at all. When you say communicating state machines, there's usually nothing in there about when these state machines get created or deleted. Well, I think for actors, they're typically...
Or like the creation, the new that typically
yes.
don't have.
Yeah.
I see, okay.
And the way you write it, so you will see the syntax of my language in a few minutes, few slides. It's just like Java. State machines, you have state machines. So like you're working with SMB, if you as a model checking person, you have to write down your program as state machines.
Nobody actually wants to write a state machine as a
Yeah.
state machine.
Exactly.
Oh, I see. So when people talk about state machines, they think about the actual thing that you type as opposed to the programming model. I see. Okay.
Yeah, you have to know some people, if you start from your specification and if they give you the spec as a state machine, sometimes in some communities it's like that, then it's okay to start with state machines. But programmers, software engineers think of a problem, they write code. They don't write a state machine,
For
You,
us, I guess, when you say state machine, you think as a semantic...
I think of it
for
as a semantic
programming
model, not
language.
that you're actually drawing bubbles and arrows.
Exactly.
Yeah.
Which you could, but that's not going to be scalable by itself.
yeah.
you have to use it in a principled way. Okay.
Yeah.
Sorry for that long.
So that's okay. That's nice to have conversation. Okay, and by friendly, I was telling you, so I mean faithful and usable. So if, I was talking that instead of other modeling languages, I wanted my language to be object-oriented, concurrent objects. I thought, okay, there's a smaller semantic gap between the real-world problems and my language then, and I wanted to have constructs for asynchronous modeling. And for usability, I thought object-oriented. This is practitioners, software engineers like it more than other type of programming or modeling. And then I was hoping that this kind of actor language be analyzable, because I was reading Aller and Hensinger books and compositional verification. And I was thinking, okay, actors are isolated. They're really loosely coupled. There's no shared variables. There's asynchronous communication, no weight. There should be, that was my PhD thesis actually, that there should be nice compositional verification approaches. Aller and Hensinger in their reactive modules, they had to have some kind of conditions over shared variables. I didn't have that. So it turned out to be really nice. We could invent compositional verification, nice compositional verification methods, and other reduction techniques like symmetry, partial order, all based on the model, at the level of the model. We didn't need to go to the level of the transition system for symmetry and partial order. So it was also analyzable. We were really happy about that. And also in Timed Rebeca, because we focused on events, again, we could have very nice reduction techniques in analysis level. Okay, and it proved to be a good choice because you guys are now using P. So that's my proof. So what's Rebeca? So this is the code, but just...
I have a question about the name Rebeca.
Yeah.
Why only a single C?
Because it's reactive object language. It's not a name of a...
It's not a name.
It's not name of a, yeah. You know, it was Alex in the beginning. It was alive object language, something like that. But then my supervisor told me, come on, your objects are not really alive. They are reactive. So it changed to Rebeca. So it's reactive object language. And this is based on actor models. We have concurrent reactive objects. And the syntax is Java. And we moved more and more and more. I started from goals actor syntax a bit, but my students pushed me through more and more Java-like syntax. It's now all Java, the syntax. And the communication is just like actors, asynchronous message passing. It's non-blocking send. And in theory, we have unbounded message queues for each Rebec. Rebec is actor, reactive object. And for model checking, we put bounds on our queues, of course. There is no explicit receive. So, and the computation is taking a message from top of the queue and execute it. So we call it event-driven. So actors are just running. There is one thread of execution for each actor. And then they're doing whatever they have to do. While they're doing that or serving a message or event, they send messages to others. They send, they're not blocked. And they're done with serving one message. They look into their queue, and they take the other message. They run the server for that message.
The question is, what's the significance of taking the message from the top of the queue as opposed to anywhere in the queue?
You can have that. In our tools, the way we implemented it now, it's queue, it's FIFO. But you can change the policy of taking your message from the queue.
So if the message delivery itself is asynchronous and non-deterministic, and the queue is not observable in any other way than getting a message out of it, then it shouldn't matter, right? In what order things are put into the queue.
We have this causality order.
Causality.
So, yeah, we have that.
Causality.
We have that. Yeah.
Okay.
So if I send you a message and then another message, we keep the order.
Oh, you do. Okay.
And we have fairness.
Yes.
So it's not lost.
Yeah.
So in the Rebeca, in the language, it also provides a mechanism to specify the dequeuing policy. So it doesn't have to be first in, first out.
Right now it is first in, first out. But it's very easy to change it to any kind of, especially now that we have time. We are thinking of earliest deadline first or any other pattern matching like in Erlang, you know. But we have never implemented that. Right now, the model checking tool is FIFO. And
I think what you said when I asked you, to me that was the important bit, was that you have fairness and causality.
yes, we have that.
Even if you say I want something from anywhere in the queue, you will still get stuff in order or not. No.
Say that again. Even if I what?
No, you could. Never mind. Doesn't make sense.
If you want to have a network which is faulty or whatever, you have to have an actor modeling that
Yes.
network that
Okay.
is messing up with the order of messages.
Okay.
And what backends do you have for generated code?
We have model checking tools that we do the model checking. We check, we check the assertions. We have CTL, LTL model checking.
But
And schedulability.
how do I execute the code? I mean, supposing I want to actually build an
We
application.
have a very old Rebeca to Java tool. We haven't used it. But yesterday I called Ehsan. He said, I'm right on it. So because after reading P, I told him, you see, that's their advantage. They can just run their code. We need that. But it's very quick. Now what we have, we get Rebeca, we map it to C++ code. So it will be mapped to just C++ classes. And it's just...
Automatically or by you?
Yeah, by our tool.
Does the tool is good?
Yeah, the tool is doing that. For model checking, we have that. But we are not, we never did the execution part of it. So we have to, it needs some effort. But it's not that much. We will have it soon, I can promise. So, and we are thinking of running it on
And how do you write
Quadcopters.
specifications?
LTL. You can write it in LTL. You mean the properties we check? What specifications do you mean?
Well, so you can write LTL.
We can write LTL.
But how do you...
But you're checking only safety properties, or do you also check liveness properties?
We can check liveness
Oh,
property.
okay.
Yeah, we can check liveness. We also have CTL model checking tool, but we never used it. And now we have timed CTL. This one we are using it. So this is very new, and we are maintaining it. And
So here's what I don't understand. So the LTL property is stated outside
yes,
the,
yes,
right?
yes, yes.
So how do you type check it? Are all the fields of each Rebeca sort of like public? You're going to have to refer to those fields, right? The state variables inside your LTL property.
Inside my LTL, yes. So Rebecs have their own state variables. There's no shared variables. But yes, as a modeler, as a specifier, you can, when you're writing your specification, you see everything. So you can have Rebec 1 variable 2 equals green, and Rebec 3 variable 5 equals red.
Supposing I created lots of instances of Rebec 1.
Okay.
How do I refer to a particular instance?
You can refer to that. You have the name of your instance. You can refer to that.
Okay.
The instance of the class.
So how are instances identified?
Okay, I have to show you the code,
Okay.
like this. So here you have the reactive class. These are the classes like router and core. And here you are instantiating R00, R01, C00, C01. So you have the instance names. If you want to, and dynamic actor creation, do we have dynamic actor creation? I think we have. These are all very new. We have dynamic topology, so now we can pass names to other Rebecs. But I'm not sure if we can. That will really mess up our model checking tool if we create dynamically.
So that's a huge difference with P
That's
then, because in P,
you have
machine addresses are first-class values.
Mhm.
You can store them in variables. You can pass them as payload messages. So it's very dynamic. The configuration of the network, connectivity changes.
the configuration is dynamic now. You can now, this is the old Rebeca syntax, it's still valid, so you have your known Rebecs here. You say which router knows which one in the code statically, but now, as you said, we can pass the name of other Rebecs in as parameter. So now you can change the configuration also. But creation is different. I'm not sure if we have creation. We have this model checking tool. We have to maintain that. So we cannot have that many. Any fancy feature that we add to the language, we have to support it in our model checking tool. So now we have this change of configuration, but not yet.
So you are saying router
Dynamic
R00, that's the name of the particular router instance.
Yeah, router is the class, and this is instantiating R00.
And then you pass R00 as an argument to the
Yeah.
constructor of R01. for
Yeah,
example.
because these are the known Rebecs. These are the Rebecs that R00 can see, the routers that it can see, the routers around it. And this is actually like this too. The binding, the topology, the configuration of the network.
So that is roughly like creating a router and passing a reference. But
Yes,
here,
yes.
the interesting thing is that here you did it only in the constructor. Can
Yes.
you also do it in an explicit message send?
Yeah, that's
Okay.
what I'm trying to say. Yeah,
Okay.
yeah. So I call it dynamic topology, just passing the names of dynamic network topology. That now we have it. But dynamic creation, so adding a router just at runtime, we don't have it yet.
Well, you just did, right? I mean, main is at runtime. When you're executing main,
Yeah, but
It
a
did happen
new,
at runtime.
newing it here, like have a new create
But how's that different? I mean, that's just like new, right? What's
For
the
model checking, you know, underneath, I can add new there, but here I have all my, you know, all my data structures there. We have them, we know.
I think I know what you're saying. You're saying that somehow the status of main is special.
Yes, and
main is
once at the beginning.
Ah, okay. Now I
Yeah.
understand. Okay.
yeah. So, okay, what I was telling you, yeah, okay, I'm done with this. And now you see this one. So here, okay, here is the class, the actor type and its message server. So you are just writing that. These are like methods in object-oriented languages. What else do I have? Yeah, asynchronous message sending. So you are sending give ACK message to your neighbor. And this is your constructor. And this is the body of a message server. And you see we don't have state machines. We have just code. And here you have instances of different actors. And these are, you pass the known Rebecs here, okay? And you have other parameters. One is, for example, one of these is the queue length. So in theory, you have unbounded queue, but for model checking, you need a bound on your queue. Okay. So, yeah, Rebeca is used for model-driven. Do you have any question here? Hope you're fine now. Yeah, you will see more later. So it's used for model-driven development. So in early stages of the design flow, and also throughout the design process, you can have your Rebeca code. It's more abstract than a programming language. And then you can explore the design space and check safety and progress also, properties and also performance. So now we have performance because we have timed Rebeca. And I will show you lots of examples, I hope. So timed Rebeca is an extension of Rebeca where we have computation time. So you can write down what's the delay, what's the computation time for executing something. You have the message delivery time, which is the network delay. So if you send a message to someone, you can specify how long it takes to get to the other actor in the network. And you can also have model periodic events. And the keywords for both of these two are after, and this one is delay. And then you have message expiration or timeout, so you put deadline. When you send a message, I send a message to you, I put a deadline. That means that that's the, like if your deadline is 10, it means that you only have 10 units of time to serve it. After that, it expires. Okay?
What, 10 units of time?
Whatever units of time, X units.
How do you measure time?
It's in model. It's a modeling language. So it's like worst case execution, you know, all those kind of stuff.
Okay, I see.
It's for a scheduling community.
So what you're saying is that 1 unit of time elapsing in one Rebec will also make 1 unit of time elapse in another Rebec. It's like the timed automata model. There's this global notion of time, and when time elapses, it elapses in all the Rebecs at the same time.
Somehow. What we say, just to be more, you know, elegant, we say we have synchronized local clocks. Because actors are distributed, we all have our own local clocks.
Sure.
And when we are doing model checking for timed Rebeca, we use that concept that I can just go ahead regardless of what you are doing. But we have that notion of global
Good.
time. So if I timestamp my message with 10, you also have 10. So
it's an interesting. So I can see, like, from what people build in terms of algorithms, that it's difficult to synchronize clocks, and it has state. So people often don't rely on that. But it's very easy to rely on your local clock to advance somewhat predictably. So, and a lot of things can be done just reading your own local clock. I mean, a lot of algorithms work without you making any assumptions on other people's clock. Still, but you want to make assumptions on your own clock, which are fine.
Yes, but even that's what I learned from Edward. They now distributed systems that you can be the clocks can be so precise and synchronized, so you no more really worry about that much. That if my time is 10, like in a car, if my time when the message to brake is sent from some ECU to another ECU, the timestamp, you can
I think I would not generalize that as.
I remember
that depends on time scales.
It depends on time scale.
The last time I talked to Edward at Berkeley, he had recently read the Spanner paper, and he was riffing on that.
Yeah.
So Spanner, maybe Jay can tell us about it. So at Spanner, is it making the synchronous assumption that that is typically not made in distributed systems?
So
Yeah.
it's making an assumption about timing accuracy, not necessarily synchrony. It's not necessarily going to assume that if you send a message, it will be received within a certain amount of time. It's if your clock says it's time t,
It's the same
it is within time t of true time.
T plus delta T. That's what Google people were telling me yesterday. Yeah, and
They
they,
have atomic clocks. So.
yeah, they were asking me about this and telling me.
I think I also went to a talk about Spanner that Phil gave, and their algorithm, almost everything about their algorithm does not actually rely on that clock.
But actually it does. It does rely on that maximum delta T. That's all this is about.
It's one part. It's about how when you do a snapshot read of your database.
Yeah.
For that part, there is like one piece where you can do faster snapshot reads. But the entire rest, like for example, anything you write is handled by two-phase commit, which is accurate without any clock assumption.
Okay. But this part that they're doing is that they are counting on some maximum delta T delay between all these distributed systems. Am I right? That's what I've heard.
Depends what you mean by delay. The clocks are off by a most delta T, not necessarily
The clocks.
messages will be delivered within a certain.
Yes.
Yeah, yeah. The clocks, sorry, the clocks, that's what I meant. So the timestamp that you see, after, if you wait for delta T time, then you're sure that you have received all the, right? Or no?
You're not sure you've received all the messages because the network could be arbitrarily. It's just that if the clock is if your clock says T, then you know that it's near T.
And
the real time is off by no more than.
And you know the maximum delay of the network too.
Well,
I think that's what you don't really
you
rely
don't know
on.
that
Okay.
because there could be network buffering. There could be
Okay.
packet drops.
So, but that's what.
Even Google can't pull that off.
I think
That's
I
right.
think that the most important part of these algorithms is that you can sort of when you know what time somebody else has, you can sort of have a guarantee that their clock will advance predictably.
Okay.
So you know that if you wait for a certain time, their clock also will have to have advanced by that amount. So you have sort of a lower bound on how far their clock goes forward. I think that's
Okay. But that's what Edward has in his tithe then. He also rely on the,
Bounded network delivery.
yeah, that's what he has. Okay, so where were we? Okay, so this is the example, the network on chip example that I showed you a part of the code. So we have this network on chip, we have all these routers and local cores, and we were working with our hardware group, so we were doing it in parallel, got all the specification from them, and they wanted to evaluate different routing algorithms, and one example was selecting the best place to put their memory in this network on chip, or choose buffer sizes, and they were using HSpice, their simulation tool. And this was the ASPIN architecture, the two-dimensional mesh GALS NOC. So this ASPIN, they have XY routing algorithm. So if you want to dispatch the packet, send it here. This is how it moves, first on the X and then on the Y. And there is also a communication protocol, which is the 4-phase handshake communication protocol. The channel is blocked until the packet arrives to the other router. So, So when you want to send a packet, you only have the input port is you only have 4 entries. So you send the neighbor, give ACK, ask the neighbor for some acknowledgement, receive the acknowledgement back. Then you can send your packet. And then when the other packet comes to be routed the same way, because this one is full, you ask for an acknowledgement. It doesn't give you the acknowledgement until it dispatches the packet and then sends the acknowledgement and get the, you can then send the packet. So this is the 4-phase handshake communication that they have. I just explained it to show you how it's modeled in Rebeca. So the exact same thing that you see in the network, you just write it down in the Rebeca code. So this is what I was telling you, the friendliness, the faithfulness of what you are modeling and the language that you have to model that. So this is what I showed you. So you have the routers and you have the cores, all that you see here, and you have all these request for send, get acknowledgement, give acknowledgement, and you instantiate your routers and cores. Okay, I showed you this already. And again, when you have this, you will just write all these message servers or methods in the body of your actor. Mm-hmm. Okay? I'm just trying to show the one-to-one mapping, how it is, the model matches the real problem. Right? Mm-hmm. Okay, and now about the time. So if you know that the computation is taking some time, you put this delay, somewhat like most of the time modeling languages, that the statements take 0 time, but then you have to model time explicitly using this delay statement. And this is that worst case execution estimation that they give you, that, okay, this computation is going to take 2 units of time. So you put delay 2 there. And then you know that sending a message to your neighbor is going to take 3 units of time. So you put 3 here. Mm-hmm. And you put the timeout or deadline on the message that you're sending. So this is how you model it. And if you want a kind of periodic event, you're sending yourself a give ACK every 10 units of time. So you take it from your queue every 10 units.
So you cannot refer directly to your local clock. You can only refer to it indirectly using the keywords delay and after.
Yes, yes. First we had this now statement, but then we took it away.
Interesting.
I mean, I think this is very much like people write this, except for the deadline piece, but this delay and after, I mean, those are realistic.
What is the deadline? I didn't understand the deadline 6. What does that mean?
This is for schedulability analysis. So actually, this has a different nature. These are for modeling. This is a kind of specification. So when I'm checking the schedulability, if I check the code and tell you if any deadline is missed. You see? Mm. So I check the code because many people are sending me many requests. I just take them, execute them, take them, execute them, and I have this deadline. And the moment any of these deadlines are missed, the model checker come back to you and tell you, okay, this one is missed. Okay. So this is not schedulable. Mm. It's for task schedulability.
The deadline between the time that the action is enabled and when it completes?
This is the deadline between when I ask you to do something and you take it to do it. Take the event to do it. If you want any other kind of, time difference, you have to model it somehow.
Can I ask you a question that's a bit of a tease?
I don't know. You ask, I will decide if I want to answer or not.
Why? Since you have this all-powerful temporal logic,
Mm-hmm.
LTL available to you, why didn't you just write the deadline thing in LTL? Why did you introduce extra syntax for it?
Because people don't like to write LTL and TCT.
So then, are you saying that you're planning to dump LTL?
No. But at least for engineers who are only looking for schedulability, okay, right. They can just, breathe and get rid of LTL and TCTL. They really hate it. Engineers hate it. Are you really recording me?
Are you? I have one more question that's a bit of a tease.
Okay.
Once you get rid of LTL, are you going to stop calling this model checking?
I'm not going to get rid of it. You are saying that. I'm not saying. we have TCTL.
Sorry.
We are not going, but we let you to use. There is a sentence for that. We let you to use what you want. You pay for what you need. Something like that.
Sure.
There is some slogan for
Pay
that.
as you go.
Oh yeah, something like that. Anyway, so if you don't need TCTL, you can get rid of it. But if you need it, we will keep it, of course. We are in a model checking community, for God's sake. So, okay. So this is communication delay. This is deadline for the receiver, and this is periodic task.
So originally, when you said deadline, I thought it had a modeling part to it too, in the sense that after the deadline, the message is effectively removed from the system. Not that that's necessarily an error. It could just be that it has like an expiration time on it.
Yes, but you can continue, but you get this warning.
Okay, warning. So you can ignore the warning if you think it's not an error.
Yes. To be honest, I don't know what our model checking is doing now, but it's easy to just, it's easy to do it. Just go ahead and have a warning. Okay, so that was schedulability analysis, and this is another way we can use our model. So they had this NOC, and they had this course here doing some stuff, and they were thinking of putting memory here or here or here. Okay, so they had 3 choices for memory placement, and then we had special kind of scenarios of applications. And when we did the evaluation, first we thought M2 is the best place because it's closest to all the cores. Can you see that? If you just draw a graph, M2 is closest to all these cores. But because there is a high congestion there, it turned out that M1 is a better choice. So when we did this kind of evaluation, and and again, okay, they could do that using their simulation HSpice tool, but it took them 24 hours while it took us 3 seconds. This is not a fair comparison probably because we have much less details, but this was a proof of concept that we showed we are telling the right thing. Even though we have much less details, it's an abstract model, we are telling the same thing, that the HSpice is coming back. Okay. Yeah, this is again showing that how we model NOC in TRebeca, the one-to-one mapping of concepts in the real world and in Rebeca, and to decide what to keep and what to abstract away, it always depends on what you want to check. So if you want to check the deadlock, there are things that you have to keep, and the rest you can just abstract away. Successful sending and receiving of packets, and estimating the maximum end-to-end packet latency. So depending on what you want to check, you decide on what to model. Any questions here? You're fine? Okay, and then we have tool support. We have model checking tool sets. We check the deadlock, the queue size. So because we have a bound on the queue, we may overflow, and we just come back telling you that we overflowed. So you can increase the bound on the queue. We have assertion checks, and then we have schedulability analysis, CTL and LTL model checking, and I should say TCTL for the timed models. And as I just told you briefly, we have, this atomic execution of a method. I think you also have that in P, right? You don't interleave when a message, when a service.
We only introduce interleaving that communication points.
Exactly, exactly. We even don't have that because the sends are not non-blocking. We don't even have that. We just, when we are done, we take the other. You know what I mean? So sends are non-blocking. Sends are not the point of synchronization. for us.
It gets tricky to even
We will
define how.
have to discuss this over lunch.
Okay. I know that in timed automata, the first semantics we built for our language, timed language, was timed automata. And for that, we need to model the cues explicitly. And then sense also became the point of synchronization. And that's why we are our state space is much more small. It's much smaller than timed automata. I hope I can get there to show you some of those kind of theory stuff too. Okay, I have to be quick. So, and yes, partial order symmetry, and yeah, and this is our tool. It's an Eclipse-based tool, and yeah, these are some just milestones and invited talks and stuff. Okay, sample projects, NOC I showed you, network protocols I want to show you, wireless sensors application. Oh, I have a lot to show you. Okay, for NOC we check the routing and dispatching analysis. I showed you also the memory placement. For network protocols, they are this kind of distributed protocols. For that, we are checking this kind of communication protocols. We check the deadlock and loop freedom. For wireless sensor applications, it was task scheduling. And track-based traffic systems, this is our new work on adaptiveness and change on the go and what we can do.
In the case of the wireless sensors application, what was the specification that they were worried about? What was the specification that you were checking?
They were the configuration of their system, the number of sensors that they have to put around the bridge, for example, and they had this frequency of checking, and they have this delays or the time that has to be spent by executing each task. So we have parameters to play with, and we came up with some kind of the best configuration.
No, I understand, but to do that, you have to ask this what-if question, right? So
the what-if is this schedulability.
The schedulability.
So all the tasks.
The deadline thing that you were talking about.
The deadline thing that I was talking exactly. So we have, I will get there. We have these nodes, and then they had to, let me get to the slides. So this is Fatima did this. I was not really involved in that. She is now an assistant professor in University of Tehran. She worked on mobile ad hoc networks. First, she was doing this using process algebra. Then she switched to Rebeca. And these are mobile ad hoc networks. When they want to route a packet from here to there, everything is changing. You don't know which route is going to, people are moving around. So you have to go forward and then come backward. You send the signal, go forward and come backward, establish the link, and then send your packet. You have this indirectly connected nodes. And the main problem in these kind of algorithms is that they may form some loops. So that was what there are other papers, I was reading them yesterday. This is what people are checking, that the main safety property is the loop freedom. And she found that. She checked the protocol, and she found loops. So they tried to improve the protocol, the performance, but then it turned out that they're introducing this kind of loop generation.
So this is AODV protocol that you're talking about. This is the internet standard, right?
Yes.
It's buggy.
It is buggy. And now they are in contact all the time. So they also checked in version 13 and 16. Bugs were found, loop is formed. So they send them the spec, they check the spec. So they are now in contact with people who are doing this stuff. I don't know if it's buggy now or not.
Right,
but
I was just curious, the version that is currently implemented
No.
all over the world, what is
probably, hopefully, they check it before releasing it. So they are in contact with Fatima, so they're doing it. I'm not involved in that, but I know that they are in contact, and they're checking this all the time. And because the model is friendly, it's easy. It's not. It's easy to change it. It's easy just to.
So who does the modeling? Who did the modeling in this?
Fatima did it.
Not the AODV guys.
No, they send her the spec, they do the modeling. Then she did the modeling. And
Why don't they do the modeling themselves?
I don't know, ask them. She knows the modeling language, I don't know. Other people, I was reading a paper, they are doing it using what? I forgot. The paper is still on my open tab somewhere. Many people are doing that, finding bugs in these kind of protocols. This is the wireless network you were asking. This is what we did with Go and his postdoc. So they had this kind of sensors on the bridges to find out if there is an earthquake. And they were doing it together with the engineering department. And they were using simulation. And of course, they knew actors very well, so that the postdoc could use Rebeca, wrote the code in 4 hours, basically. We wrote it together, and we could find out. It's more precise than simulation, because we searched the whole state space for certain scenarios, of course. So when he told us what are the scenarios, then we can search the whole state space. It's more precise than simulation, and we could find a better configuration. So these are the parallel entities. So you have the CPU, sensor and radio within each node. They are talking to each other, and yeah, the CPU has to do a lot of work, and it shouldn't miss the deadline. So that's the schedulability that we checked. Okay? And we were checking different possible sampling rate and stuff. I have to be a bit quick. Stop me if I'm too quick. And then we were comparing simulation, analytical approach, and model checking. Analytical approach is too abstract, so they have to really assume that there is everything is periodic or aperiodic or this or that, but with Rebeca, you can just write whatever you want, the exact same thing that's happening. And so they are very much pessimistic in their analysis. We are more realistic. Simulation is very much like model checking, but this is the standard difference between simulation and model checking. We are searching the complete state space. Okay, and this is very new for me. Now in Sweden, I'm working with Volvo construction equipment and Volvo cars, but this is for these big machines in Volvo construction equipment. So they have this electric side. They are making their cars autonomous, and they're using ROS. So it may be very much like what you guys are doing in Drona. So yeah, they are writing their ROS code, and we are trying to model it using Rebeca and find out the possible problems. So this is the summary. So we did verification of network protocols, schedulability in this distributed real-time sensor actuator networks, and I didn't tell you about safety performance of track-based traffic control systems. So we have an actor family of languages to do all this stuff. Shall I go ahead? Shall I stop? Shall I jump to the theoretical stuff? What shall I do? What's my timing?
An actor family of languages.
Don't look at this one. Okay, if you want, you can.
No. Let's keep going.
That will take a lot of time. So I can tell you about track-based traffic control. I can tell you about the theory of our time verification. Which one do you want me to tell you? And how much time?
Track-based traffic control for me.
Okay, how much time do I have?
You have, well, I think that you have about 5 minutes. We have been interrupting you quite a bit, so
5 minutes?
5 more minutes, yeah.
Okay. So this is another field of applications that we looked at. I was working with air traffic system control in Iceland. I noticed that they have these tracks, like in trains and like in metros. And also, this is something I didn't show you, like in this smart hubs that you can go from one place to another place using bus or bike or taxi, or this is the smart city applications, and like in NOC. So we figured out this shared pattern between all these applications. So I call them track-based traffic control. And then there is one difference. Some of them, like the air traffic and the trains, they have a kind of centralized control, while in these two there is no centralized control. So this is just, just understanding the pattern of applications. And then the project was not modeling and verifying these, but handling the change. So this is in the context of self-adaptive systems. I wanted to know if there is a storm or something somewhere in the air, how are we going to handle it? It's not planning from the beginning. So this is this kind of MAPE-K, sensor, monitor, analyze, plan.
So you're saying that the control algorithms, they are somehow influenced by the sensors.
Yes.
That are sensing weather pattern changes.
Yes.
I see.
Yes.
And you wanted to see what changes happen as a result of that. You were interested in asking what-if questions about it.
Yes, I sense the changes. So there is a storm over there. So now I have to change the routing of my airplane or the scheduling of my train. Like if in a network there is, there's lots of traffic here, you want to reroute your packet on the fly, on the run. This is self-adaptive kind of systems, okay? Like AI, this is where AI comes in. AI is everywhere, So, and first we were thinking of actors, of course, but we switched that each track is an actor and the moving objects are messages. I think that was a very nice design pattern that we came up with.
The moving objects
are messages.
The moving objects on the tracks, you mean?
Yeah, like airplanes, like trains. Now they are like messages, and the tracks are actors sending these messages to each other. You see what I mean? We just, how you say that?
I mean, but what about the control algorithms? They would be actors too, right?
It depends. It depends. In a centralized control, which is much easier, that's how I worked. I started to work with Edward, really, because he has this Ptolemy, and they have this concept of directors, which are coordinators, which are centralized control. If you have a centralized control, the coordinator knows everything about what event, or for me, what airplane is where.
Okay.
That coordinator in Ptolemy, it knows everything. Doesn't know the details, but knows what is where. So I can use that knowledge in that coordinator and have different policies for changing the plan. If it's completely distributed, I have to do something else.
So who are you working with here? Who owns this application? The Finland airspace?
Iceland.
Iceland airspace?
They are my use case. I don't know what do you mean by the owner, but they are the real world case study that we are using. They don't own it. What do you mean there?
I mean, by owner, I mean there's an artifact that you're modeling.
Yeah.
The real truth of that artifact lies with whom?
Yeah, air traffic control system.
Okay.
Yeah, it came from them. Okay. Yeah, so this is where we came up with coordinated actors in Ptolemy for handling this change, and we have this concept of model at runtime. And yeah, I think I should stop, right?
Mm-hmm. Okay.
Yeah, that's it.
Any other questions? Actually, I have a comment about that last one. I completely agree with you that this is very much in the spirit of AI and asking questions on abstract models because the reality is just so complicated that there is no artifact that represents it. You have to do modeling. And it's very interesting that you can ask these what-if kind of questions here.
Yes.
And it's ultimately boils down to some kind of a search problem. But here, it's very interesting that the same search technology is being used to ask what-if questions about a completely different application that's got nothing to do with software verification at all.
Yes, that's true.
It may be that there is an opportunity here, potentially a big opportunity.
I think so too, yeah.
I think that I think that to me the big question is, who does the modeling? As long as Fatima is doing the modeling, I think that the size of the opportunity is going to be limited.
Yeah, when they are doing the modeling themselves.
Yes, that's when the opportunities can potentially become big.
And that's why I chose a model which I think is usable. So I think software engineers just can write Rebeca really easily. And here, when you're talking about verification, you're right, it's not that much verification. So what we are trying to do is to find where the change happens, and I call it magnifier. So I just focus on where the change is happening and find out, try to contain the change and see how we can stop the propagation of the change. It's a kind of compositional verification, a mix of composition, the interface between this block that change is happening inside it and the rest of the system. It's a mix of everything. This is a very nice project, actually.
Cool. Question for you, Shah. So when you say it is them that should do the modeling, what do you think would be the reason why they don't do it? Is it because it's too hard, or is it because they are not serious enough about?
I think it's a combination of things. I think that the opportunity is speculative. They don't know that there is actually a pot of gold at the end of all this hard work.
Yeah.
The second thing is it's hard. It requires both domain-specific knowledge and modeling and abstraction skills. To me, this is very reminiscent of the situation, like 5 or 6 years ago, before the phrase data scientists became vogue, right? So these so-called data scientists, right? They are experts in statistical analysis, but that by itself is not going to justify their existence. They have to become somewhat of an expert in a particular kind of domain so that they can quickly do that kind of modeling and ask questions and do fast iteration. And I think that at this point we believe that that kind of data analysis has enough value. There seems to be consensus. I don't think a similar consensus exists here. Cool.
So,
thank you. Thank you, Martin.
Thank you. Thanks.